Okay, well, let us look at today the IV characteristics of nMOS as well as the PMOS. Okay, both we will see, and what are the important things that we have to remember while we are realizing the circuits based on the properties of IV characteristics. Okay, okay. So let me write this here. Okay. So what is the structure of the MOSFET? First of all, we have to take the bulk, right? First, we need to take the bulk. Okay. Then what is the next thing that we have to take? So very, very important one is gate oxide. Okay. On top of it, what we have to do? We have to use the polysilicon. We have to use the polysilicon. Okay. It's a very, very important structure of the MOSFET. Okay. This is called mass capacitance. Okay. So let me take the three-dimensional view of this one. Okay. We have to take something like this. Okay. All these things we can call it as this is actually the gate oxide. Okay. So let me know what is the thickness of this oxide. Okay, let me complete this one first of all. Okay. Okay. So we will see this. This is the source actually. Let us take. This is the source region. This is called the source. Okay, let me call this is the source. N plus. This is the drain. Another N plus, right? Okay. So let me take the terminals here. This is the gate. This is the gate. So this is the source. This is the drain. Right? Okay, fine. Now, a very important thing that we have to remember is what is the length of this particular area. The length of this particular area, then the length of this one is nothing but L. That means source to drain distance is L. And another important parameter we have to remember is what is the thickness of the oxide. Okay, this thickness of the oxide we can call it as Tox. That is another important parameter, right? And by default, the body is connected to ground since it is an nMOS transistor, right? Okay, because it is a p-type substrate, right? P substrate, and the source and drains are n plus. Okay, what is another important parameter? Here we have to consider VGS, gate to source voltage we have to apply. okay, in order to form inversion channel. Okay, in order to form inversion channel, we have to apply this one. In order to send the carriers from one end to another end, what we have to do then? In order to form a channel, we have to apply VGS, right? Okay. Now, if you want to allow the carriers from one end to another end, what we have to do? We have to apply the potential difference between what? Where we have to apply the potential difference. So from source to drain, right? Okay, this is called from VDS. Let me call this is VDS. Drain to source potential I'm applying, right? So the question is that, okay, as we have mentioned previously, we know that once the channel is formed, okay, by applying the potential difference between the drain and source, the carriers will move from source to drain, which means that the current is flowing from opposite direction. That is drain to source, the current will flow. Am I right? So, and this is the way that we have mentioned previously also. Okay, somehow we have not defined this exact characteristics previously. Okay. So whenever we talk about the MOS transistor, okay, we always prefer to, if you want to calculate the current, what current this is? Drain to source current. That means that we have to apply the VDS. By applying the VDS only, we will see what is the drain to source current, IDS, right? Okay. Now we need to draw how the behavior of this MOSFET between these two axes. Okay. So we are not interested to apply, by applying the VCS, what IDS that we are not going to talk about here for the time being. Just we would like to apply the VDS and find the what is the IDS. This is also called as output characteristics of MOSFET. It is also called as output characteristics of the MOSFET. If you clearly observe, the MOSFET is a 4-terminal device. Okay, you are talking about only 2 terminals so far, but definitely it should be three parameters should be required. Okay, so therefore we have to keep VGS value some fixed value, right? So unless otherwise, if the VGS is not available, there is no meaning that by applying the VDS, what is the IDS will flow. Are you getting the point? Unless otherwise, if you're not applying the VGS, there is no meaning that we are applying the VDS. Because without channel, how much voltage potential difference you apply, the carriers cannot move. Why? Because under the oxide, you will see immobile ions. Okay, it's not a free carriers. Immobile ions only will be there in it, inside of it, below that one, right? That's the reason. Okay, assume that the inversion channel is established, which means that quantitatively we can say that the VGS value is more than that of the threshold voltage. Okay, yeah. So under the assumption is that, okay, assume VGS is greater than threshold voltage of that particular MOS transistor, right? Under that condition, a channel is existed. Now we want to calculate quantitatively what is the IDS. Quantitatively, what is the IDS? Qualitatively, we mentioned previously that, okay, if you are applying the VDS, it will go and increasing. After some time, it will be constant. That's what qualitatively we mentioned. But now, by mathematically, we have to given what is the value of the IDS. Okay, mathematical equation is required for that one. Okay, we'll go and do that particular one. Right. So anyone, please let me know how do we define a current, electric current? Electric current I is equal to, okay, the rate of change of the charge density or the flow of charge carriers with respect to the time. Am I right? That is the general definition. But with respect to the MOS transistor, we are going to do the same thing with the different quantities. Okay, so that is actually called charge density, QD, charge density into velocity of the charge. What is QD here? The QD is actually charge density. Charge density. Why? Because in this particular channel, we have a plenty of free carriers are available, plenty of charge carriers that are available. Okay. How do we, what is the unit for the charge density? What are the units? Charge density of the electrons. Okay. Coulombs actually. Okay. Coulombs per meter. Per meter. What is the V? What is the small v? It is the velocity of the charge carrier. It is the velocity of the charge carrier. Okay. Velocity. Velocity of a charge. Okay. Of course, it's a carrier only. Inside of the channel, we see the carrier only. That's the reason. What is the units of this one? Meter per second. Very good. It's a meter per second. Okay. Now we have to derive this. What is the charge density within the channel, and what is the velocity of that carrier within the channel? Am I right? Based on that one only, we are able to calculate how much current available in a channel. Okay, right. Let us go and understand about charge density QD. Okay, so where the charge we are talking about, which charge that we are talking about? We are talking about the charge within the channel, right? Okay, that means, so who is responsible to get this particular charge? What is the responsible quantity that makes this charge is available? Because of this capacitive structure. Okay, because of this capacitive structure, the charge is induced there. Am I right? Okay, that means that fundamentally, since we know that the charge Q, for any charge, if you want to calculate the charge on a particular capacitor, the charge Q can be defined as the capacitance value with voltage. Okay, that means the material property of the capacitor and what voltage that we applied in order to create this, but induce this particular charge. Agree? Okay. Let us derive what is the C, what is the V here. Okay. So if you talk about this capacitor here, as we know everyone, what about the charge? What about the since charge? What is the C here? It is actually a metal oxide semiconductor capacitor, MOS capacitor. So as we know very well that this particular, the middle of this one have its own, the length of the channel is available. Okay, length of this capacitor is available, and width of this capacitor is also, we know very well. This is not W. Okay, and oxide thickness is also Tox. So these three parameters are enough to calculate C value. Okay. Okay. So fundamentally, what is the C here? The C is nothing but epsilon A divided by T. This is what fundamental equation to calculate the capacitance. So now what is this C here? According to this mass structure, what is value? Therefore, C here is epsilon. What is the area? Area of the capacitor is length into width. Okay. So we can see the width into length divided by what is the thickness of the, what the distance between the two plates? Tox. It's nothing but a thickness of the oxide is nothing but the distance between the two plates. Right? Right. Now, look at this one. Suppose if I write the capacitance C is equal, okay, if I write like this, epsilon divided by D, if I write like this, what is capacitance we can call it as? Actually, C is equal to epsilon into A divided by D. If I say area is equal to unity, then this capacitance is called unit area capacitance. What we can call it as unit area capacitance. So therefore, this normally called as, according to this particular mass physics, mass structure, it is called Cox, okay? And this is called epsilon divided by Tox. Okay, actually epsilon is nothing but epsilon naught into epsilon r. Okay, r stands for relative permittivity. Epsilon naught is the permittivity of the media, the free space. Okay, so just normally we'll take epsilon naught only, the relative permittivity of the silicon dioxide. Actually, we are taking about the silicon dioxide. Silicon dioxide relative permittivity is actually 1 unit, maybe approximately 1 actually. Okay, that's the reason why Cox is nothing but epsilon naught divided by Tox. This is called capacity unit area capacitance. So can we fix the unit area capacitance here in this case now? Right? It is nothing but epsilon ox. So Cox can we write like this into WL. Shall I write like this? Okay. Right. Okay. Now the question comes here is, okay, this is what epsilon, this one. Okay, right. So let us talk about now what is the V. Okay. So before going to the V, let us look at this one. See, the idea is that we don't want to calculate the entire capacitance charge. Okay, I don't want to calculate the capacitance throughout this charge at this moment. Okay, I want to calculate at a point X, for example, at a point X, whatever the charge density is there, whatever the capacitance is there, based on that, I want to calculate the charge. And at this particular place, how much amount of the charge is that I want to calculate, and I want to integrate throughout the length. Okay, in a particular point, I want to calculate the charge density. Once I know at a particular point the charge density, and throughout the length, if I want to integrate, then I will get the total charge. If this point is clear to everyone? Okay. Now at this point, what is the length? Can anyone tell me? It's a unit length actually. In a particular point, you cannot mention that the length is so and so. Okay, it's a unit length. Am I right? Okay. So now look at this one. If it is a unit length, then we can also call it as the capacitance C here, C for unit length, that is called Cox into W. Okay. At a point X. At a point X. Are you getting the point? Okay. Now, at the same time, I want to calculate the voltage at the point X. I want to calculate the voltage at a point X. Okay, what is the voltage actually? See, whenever we talk about this is the capacitance, it is the capacitor. Okay, so what is the voltage across this capacitor? How do we calculate the voltage across this capacitor? It is nothing but a potential difference between the top plate and bottom plate. Am I right? It is the top plate and bottom plate the voltages. Okay, what is the top plate actually? That means whenever if you want to see the charge at this bottom plate, this charge is because of what? The VGS value, right? So you can see here, I'm going to write in this way. So the voltage at this point is, let me call this is, the voltage at this point is V of X, for example. What is this at this point X? What is the voltage? V of X. That means this voltage is actually within the channel, right? So how this channel is formed actually? Because of the gate to source potential, which is higher than that of the threshold voltage, right? Okay, that means whatever the charge that you see here, whatever the charge, okay, let me write here is V of X is nothing but the potential difference between top plate and bottom plate. The potential difference between the top plate and bottom plate which must be higher than that of the threshold voltage, which must be higher than that of the threshold voltage, then only the channel will be formed. Okay. So therefore, so this is a one quantity minus of VTH. If you do it, make sure that we are applying the more than that of the threshold voltage. Okay. So this is the voltage at a point X within the channel. Okay. We know now what is the capacitance at a point X. We know what is the voltage at a point, or what is the potential difference across the channel at a point X with respect to X. That we know very well about it. Now we can see here what is the Q is here now. Now what is the charge density? What is the charge density? Charge density at a point X is equal to the capacitance at a point X, the voltage across the capacitor. As simple as that, right? What we can see here now? Can someone tell me? Cox into W into VGS minus of V of X minus of VTH. Agreed? No confusion, right, so far? Okay. Now we got a charge density at a point X. Okay. Now we need to calculate current I. What is the current I we are talking about? The current I is actually drain to source current. Okay. It is purely because of what? It's purely because of the electrons. Okay. Therefore, it is a minus of QD of X into velocity of electron. Velocity of electron. How do we define the velocity of the electron? Since velocity of the electron V is equal minus of mu n into V of X divided by, sorry, dV of X, okay? See, what is the fundamental equation for the velocity of the electron? Mu into E actually. Mu into E is actually electron. Therefore, we have to keep the minus because it's the electron, okay? Velocity of the electron is mu into E. Okay, what is the mu here? Electron mobility, right? Okay, therefore it is called mu n. What about E? E stands for electric field. Which electric field you are talking about? This means the carriers are moving within the channel, means that we are applying the potential difference between the drain and source. Because of this electric field that we are applying between the drain and source, okay, then we'll get the velocity, the carriers will attain the velocity and then move. They're able to move that one. The electrons are able to move from one point to another point because it attains the energy from the electric field. Okay. So now, so this is the electric field, right? So the electric field between the drain to source. But actually, the electric field is actually it's a derived quantity from the physical quantity that we applied. Okay, what we have applied? So VDS we have applied. So since the potential difference between the drain and source, that results the electric field will be developed. Because of that electric field, the carriers can move. Okay. Okay, right. So what about this one? Can anyone help me? Therefore, it's mu n. It is nothing but d v of x at a point x that we are talking about. Okay, into dx. Okay. So VDS stands for here. What is the VDS here? The potential difference between the drain to source. That means we are talking about at a point X we are talking about, right? At that point, what is the potential we are applying? V of X. Okay, right. Now, this is what we are talking about. Okay. Now let me write this is, if we substitute these two things here, what we'll get? What is the Q of QD? Cox W into VGS minus of V of X minus of VTH. Okay. Now what about this? Into minus mu n dV of X divided by dx. Okay. Now if you do some kind of mathematics, if you minus minus will get plus. Therefore, you keep this IDS into dx here, and this is mu n Cox into W into VGS minus of VFX minus of VTH, right? Agreed? Right. Now, so this is what we calculated, something which is at a point X within the channel. Did you catch this point? This is the value of the IDS at a point X within the channel, right? Okay. So now we are going to use the integration between this one throughout the channel, right? I'm applying throughout the channel. And one more thing is that, so throughout the channel, what is the potential? This side actually, what we can see that, see here we can see that the distance, right? X stands for the distance. Here we talk about this one is voltage, okay? So therefore here the distance means that 0 to L integration, we have to do it. At the right hand side, it is a voltage. Therefore, we have to integrate with respect to voltage, okay? 0 to VDS value. 0 to VDS value. Look at this one. So for example, if you look at this particular capacity, the voltage within the channel, you carefully, we can observe V of X value at X is equal to 0, what value you can observe? V of X, the voltage at a point X near to the source, what you can see? Usually, this is, in the previous class, we have mentioned that this is actually connected to ground, right? And this is connected to some potential, right? We apply some potential here, right? This is called VDS. Okay. Now, what is the value here now? 0. So now what is this value? V of X at X is equal to L. L means this is the 0th distance, and this is the X distance. That means which is near to the drain. What is its value? VDS simply. Okay. So whatever the drain to source potential is there, that potential is nothing but the VDS. So near the source, we have a 0 potential. Near the drain, we have a VDS. Supply is available, right? So under this condition, I have mentioned that V of X can take either 0 or VDS value, right? Now, if you integrate this one, what you will get now? IDS into L is equal to mu n Cox W into VGS minus of, if you integrate this one and apply the limitations, everything that we have seen in the last class, directly I'm writing this one, VGS minus of VTH into VDS minus of VDS squared divided by 2. Just a simple integration part, just I have taken that directly, and granted I'm doing this one. Okay, now IDS value, what is the IDS value? IDS value is equal to mu n Cox W by L into VCS minus of VTH into VDS minus of VDS squared divided by 2. It's a very, very popular expression, right? Okay, what we call this particular equation? This equation is nothing but a linear current equation of an nMOS transistor. Why it is a linear equation? Why it is a linear equation? Because if you see IDS, if you write IDS versus of VDS, it is a linear relationship between them. Okay, if you see that I is proportional to that of VDS value. Okay, okay, you can see this IDS value is proportional to that of VDS. As we keep on increasing the VDS value, IDS will also increases proportionally. Okay, that means what you can expect here in this case now, if you talk about this is the characteristics between VDS and IDS, what we observe according to this one, if the, okay, as we have mentioned that the VGS value is a finite value, it is more than that of the threshold voltage. That's what we have assumed previously, right? At the starting of the class, what we mentioned, VGS value is more than that of the threshold voltage. Okay. Now, if we keep on increasing this VDS value at a particular value of VGS, at a particular value of the VGS, okay, and if you keep on increasing the VDS, then it is linearly increasing the current. Oh, so sorry. It's a linear increase, right? It is a linear increase. Okay. So therefore, as we keep on increasing the VDS value, IDS also will increases in the same way. Will it go as it is like this? That's the question. Okay. So actually, unfortunately, it won't be happening. What is the reason? What is the reason why this cannot go the linearly forever? Okay. Look at carefully here. If you talk about this is the mass structure, this is the N plus, this is another N plus, this is the oxide. On top of it, we have a polysilicon. Okay, so we applied a potential difference here. What is the potential that we have to apply here? And what is the potential we have applied here? This is the drain source and this is the drain, for example. Okay, so it should be less, right? Less voltage we have to apply here, more voltage we have to apply. Are you agree with me? Or that means we have to apply a positive potential at this place. Here we have to apply a negative potential at the source. Okay, why? If it is a negative potential at the source, they can pull the electrons from source side to the drain side. Therefore, drain can collect all the electrons that are available coming from the source, right? That's the reason why you should have a positive potential. This should be a negative potential. Okay, fine. Now, if you keep on increasing the more and more positive, what will happen at the drain side? If you keep on increasing the more and more positive potential at the drain, what will happen? As you can see, actually, the source is actually, most of the cases, it's a grounded actually, right? Okay. And source and body is also at the same potential, as I mentioned previously also, okay? Since the drain is also, substrate is also at the same potential, substrate is also at the same potential, that means it is simply that drain to source is equivalent to that of the drain to body, one and the same. Drain to body is nothing, drain to source is nothing but drain to body. That means you can see the drain is a positive potential we are applying here. This is actually a negative potential we are applying here. What is the biasing here actually? Initially, because of this one, channel is formed effectively. If you increase the more and more and more and positive potential, then what happened to this particular depletion region of this N region? It will increases. Okay, agreed? So therefore, this will be increases some more, something like this. This is what the depletion region will increases. Since it is actually a reverse bias actually. Drain to body is reverse bias. If the reverse bias is increases, these carriers cannot see here, right? You cannot see these carriers here. Depletion region is nothing but what? Free of free carriers. Okay, there won't be any kind of carriers. Therefore, if you keep on increasing this particular source potential is lower and lower and increases the drain side more and more, then what will happen? This is what is happening here. At the source side, more charge is available, and towards the drain side, less charge is available. Especially at the near to the drain, you can see there is no channel at all. So what we can call this particular phenomenon, what we call it is pinch off. Okay, pinch off is occurred near the drain. So therefore, what is the pinch off? Pinch off is nothing but there is no inversion charge near the drain because of the more and more positive potential we are applying at the drain. Okay, so that's the reason why even if you are trying to increase the VDS value more and more, it cannot go linearly. Instead, the value of this one will be constant, something like this. It will be constant, something like this. So this is for a particular value of VDS. Okay, let me write very clearly. It's not a just not good way. Okay. The question comes here is that what potential? So that means this question is that what is this potential will do this kind of phenomena? That means that the voltage of VDS at which this pinch up will occur. Okay. So I hope everyone can understand that this is called the linear region. This is called the linear region. Okay. This now, if the IDS value is not following the VDS, or IDS is independent of the variations of the VDS, then this is called saturation region. This is called saturation region. Okay. Okay. So the question is that what is the point at which this is happening is the one thing. From linear to saturation, what voltage is responsible? Someone, can you please identify? Hmm? What voltage that is responsible to find this particular one? That means we want to have a drain potential, right? We want to have a drain potential. Okay. If this drain potential is less than that of the gate potential and threshold voltage, if this is less than this particular one, whatever the drain potential that you apply, which is less than VGS minus of VTH, I'm so sorry, it is more than that of the VGS minus of VTH, then pinch off will occur. Okay, so you may ask the question, what is the reason why? Okay, let me call this is also source. Why this has happened? So look at this point. So here, what is the condition for creating a channel? VGS must be greater than VTH. Must be greater than VTH, right? Okay. If it is less than VTH, what will happen? It won't happen. So look at this point. Look at this point. Here, what is happening? The drain potential is more and more. Okay. At the drain side. What it makes actually, it makes near the drain, the channel will be depleted. That means that there is no channel at all. That means the voltage at that point is actually less than that of the threshold voltage. It should be less than that of the threshold voltage near the drain. If you're increasing the more and more and VDS value at the near the drain, therefore that value of the VGS minus the VTH is the gate to source voltage is less than that of the threshold voltage. Okay, so that's the reason why. So this will happen. As I can say that okay, this is the point that we can call it as VGS minus of VTH. This is also called as overdrive voltage. Normally, people will call it as overdrive. In the terminal point of view also, we can say one thing. Of course, when the VGS value is less than, if it is less than, okay, it is stands for saturation. Okay, when the VDS value is less than VGS minus of PTH, which means that the channel is inverted near the drain also. Channel will be inverted near the drain. That is, whatever the potential that you can see is more than that of the gate to source voltage. Okay, therefore definitely it is there in the linear region. Okay. Now we want to calculate what is the value of the IDS at the saturation. What is the value? Just we have to keep this, it is more than, or okay, if it is also possible to say that VDS value is greater than or equal to just one threshold less than that of the gate also, so more than that of the gate also, it will increases. Okay, or we can say something like this. What is the minimum value of this one? Let me call this is, okay, since the source are it's common, let me take the sources aside. Okay, I don't want to bother about this one. Just simply VD, and this is VG minus of PTH. Okay. If you keep what is the VDS? VD minus of VS. What is the VGS? VG minus of VS. VS will get cancelled. Not a problem. Okay. Now, if the drain potential, it is also inherently say that if the drain potential is one threshold less than that of the gate. Okay, that means if you reduce one threshold within the gate, then whatever the voltage that we see, that is responsible to get the threshold voltage. Or I can say something like this also. If the drain potential is just above one threshold than that of the gate, when compared to the gate potential, the drain potential is one threshold above, then the transistor will enter into saturation region. Okay, just one threshold is enough. Okay, so therefore that's the reason why. Therefore, we can say that therefore VDS is equal to VGS minus the PTH. We can substitute. Okay, in the given linear current equation, just substitute in place of VDS. It is nothing but VGS minus the PTH. Okay, so now what we can write it here now. When VDS is equal to VCS minus of PTH, then IDS is a saturation current. Saturation current. As you can see here, quickly substitute this one. IDS is actually one. Okay, sorry. Let me write mu n Cox W by L into VCS minus of PTH into VDS minus of VDS squared divided by 2. Okay. Now, what is the in place of VDS? What we would like to substitute VGS minus of PTH. It becomes VGS minus of PTH minus of VGS minus of PTH whole square divided by 2. Therefore, it is simply 1/2 mu n Cox into W by L into VGS minus of PTH. Therefore, it is evident that the IDS value is independent of VDS. In this equation, you don't find any kind of VDS, right? That's what the characteristics is showing. Okay, when the VDS value is equal to increases beyond the VGS minus a PTH, therefore the current is independent of VDS variations. Okay, so that's how we can say the IDS value is in this way. So this is called saturation current equation. Okay, another current equation is also there. That current equation is called cutoff. IDS is equal to 0. Therefore, this is called cutoff. Cutoff region. The MOSFET is set to be in cutoff region. It is in saturation region. Okay, it is in linear region. MOSFET is said to be in linear regions. Okay. Yes, hopefully we have cleared everything. Okay. Always remember that one MOSFET is operated in 3 region of operations. One is cutoff region. That means that what is the condition? Let me conclude and summarize this one. What is the conclusion? So when VGS is less than VTH, then then what we can call it as IDS is equal to 0. Okay. When the threshold less than threshold voltage, channel cannot form. Whatever VDS you apply, no current will flow. It is called this one. This is called cutoff region. The MOSFET said to be in cutoff region. Okay. Now, when VCS is greater than or equal to VTH, inversion channel will be formed. Under this condition, if the VDS value is less than VGS minus of VTH, then what will happen? What will happen? Then IDS is equal to mu n Cox W by L into VCS minus of VT into VDS minus of VDS squared divided by 2. Okay. So this is called, what this is called? Linear region. Linear region. The last one, okay, it's mandatory that VCS values must be greater than or equal to VTH, undoubtedly. And now, when VDS value is greater than or equal to VCS minus of VTH, what we can say? IDS value is equal to half mu n Cox W by L into VCS minus of VTH whole square. So this is called saturation region. Saturation region. Okay. So you always remember these are the fundamental equations when we talk about analog IC design. Whenever we are using the MOSFET, we need to know about this one. Okay. We'll do some kind of exercise problems on this particular thing. And tomorrow we will see about the PMOS structure also and what is current equation, how it will be different than these particular equations, and we'll see some problems as well. Okay, we stop here. Thank you.